Welcome everyone. In this video I'm going to show you the final version of my thermostat. So this thermostat is used to control the temperature on the cold side of a Peltier cooler, and for demonstration I will use this TEC0706 Peltier cooler with now passive cooling on it. So I just use this huge heatsink to cool the hot side. The purpose will be just to demonstrate this thing, how it works. So I have a few videos already where I was building this thing, and I was experimenting with this SZBK07 300 watt DC-DC buck converter. So the purpose of this buck converter is to convert the input voltage to some sort of output voltage, and then that output voltage and current is controlled by two potentiometers which are placed on this now empty spot. So originally we had two of these 100 kOhm potentiometers here, these streamer potentiometers, and then I removed them, and actually this is a bad board. I just use it for the demonstration. So what I did, I used a 10 kOhm resistor connected to the 2 and 3 pins which are wired together because this is used as a rheostat. So I connected a 10K resistor there, and then that resistor is connected to a digital potentiometer, and that digital potentiometer is controlled by an STM32 microcontroller, a blue pill. But alternatively you can control it by an Arduino. And the code that I'm going to demonstrate to you is compatible with both systems. So when we inject the voltage here or current here, that will change the voltage value which reaches the feedback pin on the controller chip here, and that will regulate or adjust the output voltage of this board. So then I combined all these things together. So the basic strategy is that we measure the temperature with an NTC thermistor. So this is a resistor with a negative thermal coefficient. So the resistance is decreasing when the temperature is increasing. So what is happening here is that this is inside a voltage divider, and we read the voltage, the output voltage of that voltage divider with the STM32, and based on that we can calculate the temperature. So we get a feedback from something that we want. This is a universal thermostat basically, but we will use it with this. So we read the cold side temperature with this thing, and then based on the logic that I programmed, we will increase or decrease the output power on this board. Therefore, the connected Peltier cooler will have a colder or warmer cold side. And basically that's all. And how I implemented this thing is the following. So everything is in a microcontroller, and most of the things can be changed by the user by using the rotary encoder and the button. So by using the rotary encoder we will step in a menu. I have a video about this, so let's check the corner up there, and you can see how to implement that thing, but I will tell you also when I demonstrate the code. But we move in the menu, and whenever we want to change the value of one of the menu items, we just press the button and then we turn the knob again, and that will change the value. And everything is pre-programmed, so the step size for the change and the increment and everything, but you can change it when you work with the code. But I think it's better if I don't talk about this, but I actually demonstrate it. So I just assemble everything and I show it to you. But before that, I just want to show you this thing. So we have a 20 by 4 LCD here. So 20 characters can be printed in one row, and we have 4 rows. So this is a rotary encoder under this knob. We have a simple button here. For some reason the mechanics is not so good, but yeah, it works. Sometimes I have to press it twice. We have banana plugs. This is the output. So basically the output of this converter is here. Here the cable for the input power is already, let's say, installed in the box. So this is like a permanent solution here. We don't need to have connections here or something. So this cable goes to the input of this board. And then we have a very long USB cable. So the microcontroller is situated here. And then, yeah, we have the NTC here, and that's all. And as you can see, this panel here is 3D printed, and I can tell you why. I really hate cutting the shapes because I cannot cut them precisely and nicely. So I thought that I can just cut a rough outline for the holes and all the screws. I can drill these holes, but then I can use, for example, Fusion 360 and design the front panel precisely and print it more or less precisely, and that's all. There are some flaws here and there, and that was caused by the fact that I ran out of the filament during the printing. So the printer went a few lines within one of the layers without actually extruding anything, and I was a bit clumsy, so I could not replace it properly. So part of one of the layer is missing in this corner, but otherwise it's a solid stuff. So let's connect everything, and I can show you some more interesting stuff. So I joined everything together except the USB cable that is not plugged in. I tilted this box a bit backwards, so I put something under it, so you will see the screen properly. So we use these rubber bands to push the NTC on the top of the Peltier cooler's surface. So this is the cold side. The wires are connected here. This connection is going towards power supply. I will set it to, let's say, 6 amps as a maximum output current, because this is a 6 amp per unit. And I will set the output voltage, or limit the output voltage, to 14 volts. And that should be enough. So let's plug this in and see how the display looks like. So you see some startup message, hopefully. And then you see the display. So on the first line, or in the first line, you see that it is off now. The temperature is constantly measured, and it's updated by this interval here, which is 500 milliseconds, so half second. So you can see that twice in a second we get this value updated, and you can see that if I touch this, it goes up. So it works. So this is showing you the status of the cooling or the regulation. This is the actual temperature measured by the NTC. Then we can set up a goal temperature. That's the goal here. Now it's 30 degrees, but we will change it soon. P here is the power expressed in percent. It's basically just whether it is going full power, half power, or something like this. And that is always a relative number. So if you have different input values here, then you will just know that, for example, if this shows 50 and let's say your input voltage is 14 volts, then the output voltage is around 7 volts and things like that. So the update interval is defined in milliseconds, and it can be changed by 100 millisecond increments. And the update interval is basically valid for everything. So the temperature measurement, the update of the power values, and so on and so on. And then the tol is the tolerance in Celsius degrees. So when we measure the temperature, we have to decide whether we should increase or decrease the power or keep it at a certain level. And when we reach the goal temperature, then the tolerance will define whether we have to turn it off or turn it on. So if we reached, let's say, the 30 degrees already, and we are, let's say, fluctuating between 30.1 29.8 or something like that, we don't do anything with the power, we keep it at that level, which was enough to have the temperature. But when the temperature goes, let's say, beyond 31, then we know that we need some extra cooling, so therefore the power on the output will be increased. So I show you that if I turn this thing, you can see that that small arrow jumps. So this is basically how we navigate. We can navigate backwards as well. So the goal temperature can be changed if I press this button. And as I said, this has some mechanical issues, but yeah, I could not be bothered by changing it. So when the icon here changes to X, then we are in the menu in that certain line and we change the value. So now you can see that I can decrease it. And I wrote the code in such a way that whenever I do something with the rotary encoder, the numbers are, and only the numbers are updated. So that's like quite convenient. And you can see that it gives you an instantaneous result. So let's say we want to reach 15 degrees. So we approve it. And then update interval is fine, and the tolerance is fine. So all I do, first I turn on the power supply here, and hopefully everything will be all right. And now I allow the cooling. So I turn this on. And we can see that the temperature is slowly decreasing and the power is increasing. So now the temperature on the surface here is going down more and more, and as long as we don't reach the goal temperature, which is 15 degrees on the surface of this thing, then the power will be increased. And when we are within the tolerance, which is defined here, so 1 degrees plus minus 15 degrees, we stop. So soon this will stop. So now we are within the tolerance. And now the software will see that we went out from the tolerance towards the negative levels, so it will decrease the power. And why this happened is because we are updating too quickly, and there is a so-called thermal inertia in the system, so it will not jump immediately to the temperature. The Peltier cooler will need some small amount of time to reach that temperature. Therefore, if you try to update this value too quickly, it will result in a big overshooting, and therefore the program will suffer a little bit and jump up and down until it finally finds the correct amount of power. And this is one of the reasons why I implemented the update interval as a user option, so the user can change it, because this should be decided basically during the experiment. So you have to run an experiment before actually knowing your system, and then you will see that, okay, 500 milliseconds might be a bit too quick, so you can decrease it. In some previous experiment, I did this updating in every 2 seconds, and that looked quite okay. But again, it really depends on what you have here. If you have a large volume, for example, you measure something here and you feed the cooling here, there will be some time when your system, let's say, settles down at a certain temperature, and you will need to be aware of this. So then you might need a very long interval. But if you have like a very tightly packed system in a very small volume, for example a metal block or something which can pick up the temperature change very quickly because it's a good conductor, then you can decrease this interval. And now you see that we started to reach more or less the power that we want to go for. So of course the value is not like super stable, but you can see that now we are at 14 as the power value, and that is pretty much fine to keep the surface within the tolerance. So now we are not changing. And now I'm doing a very simplified thing with the NTC, which should not be done actually, but I'm just reading one single value, and based on that I decide what to do. But if you would use this in a more critical application, other than just sharing some ideas with friends, then you should take an average of, let's say, 10 readings, because you can see that sometimes this actually jumps out of the range, so to speak. So sometimes this temperature was 13 degrees for a moment and 17 degrees for a moment, like you saw it now, it was 16. So that can confuse the logic in the software. So now you can see we are at 15% power, and we keep this thing at 15 degrees. And I don't know the voltage, but I can see on the power supply that this thing now draws 0.18 amps, so quite small performance, and we already at 15 degrees on the surface of the Peltier cooler. But I have to emphasize that this is just the surface of the Peltier cooler. As long as you put something on it, or you put some, let's say, thermal load on it, so when you want to cool down like a big bowl of water or some larger volumes, the Peltier cooler will need much higher power input to have the same temperature. But yeah, this was basically the demonstration. You can see it works nicely, and finally I could put it in a nice enclosure. I think it looks quite okay. But maybe in the future I have to revise my strategy for picking boxes, because this was just fine size, but maybe I should not put too many things in such a small box. So yeah, so you could see that this works, and it works quite okay. So let's go to my computer and check the code behind this thing. So let's go through the code, and I will go through the code quite quickly because I already explained a very similar code. So I just tell you those things which are more typical to this application. But for previous versions and maybe more detailed explanation, check the corner up on the right side of the screen, and you will see a link there. So we have to use the SPI because of the digital potentiometer, so you can see the pins for the STM32 blue pill and for the Arduino. So connect those pins which are needed for your particular microcontroller. And then, as I said and showed, I'm using the 20x4 LCD. So we use the liquid crystal I2C library, and you can see the SDA and SCL pins defined to STM32 and defined for Arduino. So these are the two most important hardware, so to say. And then we have a menu counter, so this will count from 0 to 3. So we have 4 different menu items, and this will keep track of them. And then we have menu to value. So instead of naming the variables here as goal temperature or update interval or tolerance, I just kept these values. And why? Because in the previous video where I showed you how to build a nice menu and how to navigate and change the values and so on, I was using these variables, and I was thinking about, okay, let's recycle that code. So instead of renaming all the variables, I found it more easier just to keep track of the names, and then I know that the menu to value will keep track of the goal temperature and so on. So yeah, sorry if it's confusing. But yeah, we start at 30 degrees, and we will change that value. The menu 3 value is the update interval, and you will see all the default values here. And then the menu 4 value is 1, so this is the tolerance, and you can see that that's 1 degree Celsius. So nothing is selected, as you can see, so all these variables are false. Then we have a boolean for the cooling is on, so this is very self-explanatory. So if we have the cooling off, then this is false. Power percent, this goes from 0 to 100. Cooling power, this is also goes from 0 to 256. So basically the power percent is calculated based on the cooling power. So we see what is the cooling power value and how is that related to 256, which is the full range of the potentiometer. And based on that, we calculate the percent, and that's all. And then we define some pins. So as we know, we have 2 pins for the rotary encoder, and I was using a rotary encoder which does not have buttons built in. So there are only 2, so to say, output pins on it. So I connected these rotary encoder output pins to the PB3 and PB4. And this is on STM32, where you can use most of the pins as interrupt pins. But if you are using Arduino, keep in mind that you can only use the pin number 2 and pin number 3 if you have the Nano or Uno, for example. And then I have a separate push button that is connected to PB5. The V out pin, which is the V out of the voltage divider coming from the NTC, that is the PA0 AD converter pin, and then we have the chip select, which is the PA4. So this is all. And then these statuses are needed to keep track of the rotation of the rotary encoder. Then we have to refresh the LCD, refresh the selection. So when we move the cursor and select a menu item, we will change this arrow to an X. We use time values, and I just call them time now 1 and time now 2. We will store the millis in them and keep track of the update interval. Then we have the thermometer related variables. We have to know what is the power supply for the voltage divider. In our case, this is 3.3 volts. Then this variable stores the value of the voltage divider, the output value of the voltage divider. We calculate the resistance of the NTC based on the output voltage, so we have to store that as well. We have to measure the 10K resistor that we put in the voltage divider, and for me that was 9,840 ohms. And this is the B parameter for this particular NTC. This is needed for the formula that we use to calculate the temperature. And we have T0, which is the T0 in Kelvin. And the formula gives us the temperature in Kelvin, so we store it in Kelvin and then we convert it to Celsius. So this was basically the beginning of the code. And then we go to the setup. So as you can see, the switch or rotary encoder related buttons are internal pull-ups, and they are chosen as it is. Then we know that the chip select is an output, and an analog input is chosen for the AD converter. Here, there's nothing to explain. We initialize the LCD, write some random data, and wait 5 seconds. And then we clear the LCD before printing an entirely new thing. These are the stationary things which are never changed, and that's all. And here we just store the current status of the rotary encoder, so we know what are on the outputs. We have 2 interrupt pins. One is used for the rotary encoder, and the other is used for the push button. And for the rotary encoder, we look for a change in the value of the pin, and here in the button we look for a falling edge. And finally, in the setup, we just send a 0 value through the SPI to the digital potentiometer, so it will be on the highest value, because I wired in such a way that if you increase the value of the potentiometer from 0 to anything which is larger than 0, you will decrease the output voltage. And this is because how it works with the DC-DC converter. So then the loop is relatively simple, and let's just very quickly go through it. So we check the time, and then we see this condition, and the -3 value is our update interval. So if we are if there is more time elapsed than the update interval, we step here, and we have to see that any time when we step into this, we always measure the temperature and print it on the LCD. And if we also have the cooling enabled, then we adjust the temperature and write the potentiometer. So based on the temperature reading, we decide whether we should increase or decrease the output power, and based on that decision, we write a smaller or larger value on the potentiometer, which will either increase or decrease the output power from the DC-DC converter. And that's all. And before finishing this if part of the code, we write the time to the time now to again. So basically we zero out this thing, and we start over and we count again until we have the required amount of time elapsed again. Then with every loop of the LCD, we see if we have to refresh the LCD. If we have to refresh, we update the values, and also we have to see whether we are in a menu or not. So basically, if any of the menu items are selected, we don't do anything, so we don't move the cursor. But if the menu items are not selected, we are in the main menu, that means, so we have to move the cursor. So that's what happens here. And at the end, we have to switch this back to false, because this is always changed by the rotary encoder. So then we have to wait for the rotary encoder to become rotated again. So then this refresh LCD becomes true, so the code will enter this part again. And also we have to see if the refresh selection is true or not. If it's true, then we update the selection, and I will show you what this does. And similarly to the other previous part, we have to make this false. So basically this part is a rotary encoder related thing, and this is a button related thing. So this means that if we selected a menu item, then the arrow sign becomes an X, and we will know that now we are not stepping in the main menu, but we are changing the value of one of the menu items. So I explained this part a million times, so I just very quickly go through it. So we don't care about the first menu item because that's just the on-off. So we don't have to rely on the rotary encoder. But if we move to the second one, we just look for the changes of the rotary encoder here. So we can see whether it is moving in a clockwise or counterclockwise direction. And based on that, we increase or decrease the value. So these are defined by us. So you have to see what is the maximum value and what is the increment. So I chose 30 degrees as the maximum value for the temperature. Since we go always in the cooling direction, this is like the absolute worst case that we can have when we want to cool with a thermoelectric cooler. Because with a thermoelectric cooler, our goal is always to go below the room temperature. So if the room temperature is 30 degrees, then we don't do anything, but yeah. So we see that if we are smaller than 30, then we can still increase the value, otherwise we just stay at 30. Actually, this can be left empty, so it's not reset, but yeah, I just left it as it is. Then, if we are decreasing towards -30, that's the minimum, so the lowest value that we can reach. And here in this part, if we are smaller than that, we don't do anything. So I can even delete this, but I just keep it at -30. Otherwise, we keep decreasing it. So if, for example, the temperature is 15 degrees plus 15, this will not be true. So we enter the else branch and we can go down by 1 decrement, which means that when we rotate the rotary encoder, the next value will be 14.9. So that's what's happening here. The -3 is the update interval. So I'm not going to explain this more, but the maximum update interval is 1 minute. So 1 minute will be between 2 measurements and 2 adjustments for the power supply. And the increment can be changed by 100 milliseconds, and the smallest value is not 0 but 100 milliseconds. So that's a very rapid update. But as I told it during the experiment, quick update is not really desired and not really practical, because we need time to have the heat spread towards the cold side of the thermoelectric cooler. So the thermoelectric cooler cannot remove the heat so fast. So this can lead to some sort of thermal runaway or something similar process when you update the values too quickly, but your system is not able to catch up with the increased cooling. So yeah, that's what we do here. And then the final menu item is the tolerance. So the tolerance is defined between 0.1 degrees to 10 degrees. So if you are within your goal temperature with this value which you just defined here, then the cooling will stay at the certain value. And yeah, 10 degrees is maybe not a smart choice. And 0.1 also for the increment or decrement size might be too small, because I actually calculated the resolution in a previous video, and that was something between 0.2 0.3 degrees Celsius. But yeah, let's just keep it like this, and you can change this value anytime. And then after going through all these else if things, so what should happen if we are selected a certain menu item, there is an else at the end. And that means that if none of the menu items are selected, and that means that we are in the main menu. So we are just changing the menu counter between 0 and 3, and that will just switch between the different points in the menu. So that's what happens here, whether we move in the positive or negative direction. So push button function is coming from one of the interrupts, and it's basically just we see what is the menu counter's value, and based on that we just flip the state of that. So if it was enabled, it will be disabled, and if it was disabled, it will be enabled. It's very simple. And then we refresh the LCD and also refresh the selection. So when this is refreshed in the next iteration of the main loop, the selection will be updated, and the small arrow becomes an X, like this here. This is the print LCD, which is called in the setup. So as you can see, these are the stationary things. So like off, temp, so on, so on. In fact, the off is just the initial value that will be updated, but yeah, the others are all stationary. Update LCD, so these are the updated values, and we have 3 values which we update here, and these are based on the user input. So when you rotate the rotary encoder, you can change the goal temperature, you can change the update or refresh interval, and the tolerance. And then when we rotate the rotary encoder, we change the position of the arrow. So what we do here is first we clean up everywhere, because we don't know where is the cursor. So we clean the first block of all the 4 lines, and then we see where the menu counter is located. So whether it is 0, 1, 2, 3. And based on that, we redraw the arrow. So if it is in the first line, then we draw the arrow there. If it's in the third or fourth line, then we draw the arrow there. So that's simple. And then the update selection, so that's when we push the button. So we see, if we push the button when we were standing at the 0 value of the menu counter, then first of all we change the cooling, so we don't know if it was on or off, so we just change the value to the opposite of its previous value, and then we go for an if-else, and we see if it's true, then we print on. If it's false, then we print off. It's simple. And with the other, we just put an X in front of the menu item, and then we will see that, okay, that thing is selected. So when we will rotate the rotary encoder, those values will be changed or updated. So in this function, we have the temperature conversion. So the output voltage is this when you are using a 12-bit resolution AD converter and you are feeding 3.3 volt to the input of the voltage divider. If you are using Arduino, use this expression in the parentheses. And then based on the output voltage of the voltage divider, we can calculate the resistance value of the NTC, because we know our 10K resistor, the other resistor in the voltage divider. We know the supply voltage, which is the 3.3 volt, and the output voltage, which is just obtained from the AD converter. And then we can substitute this value into this formula and get the temperature in Kelvin. And then we change or convert the Kelvin into Celsius. And then we update the LCD with the Celsius. So we know what is the temperature read by the NTC. And then this function is very simple. This is the function that communicates with the digital potentiometer. So chip select pin goes low. We send a command with this value, and then we send the cooling power value, which is between 0 and 256 or 255. We wait a little bit, and then we switch back the CS1 pin to high. And then we can calculate the nominal voltage based on this formula. So I just left this here because you can use this nominal voltage, print it, or just use it for something else. So yeah, feel free to use it. And then finally, this part is the main logic behind this thermostat or adjustment of the power for the Peltier cooler. So first of all, we check the tolerance-based value. So if the absolute value of the difference of the actual temperature and the goal temperature is smaller than the tolerance, then we don't do anything. So the power is at the proper value, and therefore the temperature is kept at the desired temperature plus minus the tolerance, so we don't do anything. Otherwise, we have to see how is the temperature is situated as compared to the goal temperature. So if the red temperature is larger than the set temperature, and we still have space to increase the cooling power, we increase the cooling power by 1 increment. Otherwise, we don't do anything. So if the cooling power is larger than 256, we just cannot do anything. And then, if the other is true, so that means that the measured temperature is smaller than the set temperature, we already cooled more than it's necessary. So if we can still decrease the cooling power, because it cannot be lower than 0, then we decrease by 1 decrement. So less cooling is applied on the Peltier cooler. And then at the end of this function, we calculate the percent. So this is basically the percent value. And then we put it on the LCD. And you can see that there is just 1 unit or 1 smaller block which is updated. And basically that's all. So you could see that the logic is quite simple behind this thing, but it requires some different devices to work together and know about each other. So I'm talking about the LCD, the rotary encoder, the button, the small voltage divider, and then the maybe most important part, the digital potentiometer. So with all those, you can make this work, and you can see that it's not that difficult. So I hope that you liked this video. I think this is the final video for this kind of cooler and this kind of thermostat, because I think now it works as I wanted to make it work. And also I put it in a proper enclosure and everything. The code looks fine for me, and I tested it and it works as I want. So this is all. I hope you learned something. Please don't forget to subscribe. That would help me a lot. You can also donate if you want, or if you feel that this was extremely useful for you. And if you want to have more questions about this topic or want to discuss something, please feel free to leave a comment. I'm really happy to read the comments and discuss different things with you. So basically this was all. So once again, I hope you learned something. I hope this was useful for you, and see you in the next video.